section, we're going to take a look at vectors. Okay, we're going to spend a little bit of time here specifically looking at vectors and the idea of what a vector is. And if you recall, when we've been talking about displacement, we've been always saying positive or negative. Like if I walk this way, it's positive displacement. But if I walk this way, it's negative displacement. So you're giving a direction, positive or negative. If I knew the velocity at which I'm walking, I could say, ready? I'm walking at 1 meter per second, positive, or east. Not in the city east, but east is in right, west is in left. Or now I'm walking at negative 1 meter per second, or simply 1 meter per second west. A vector is what we're going to talk about now, and that's what that is. So first, to define it, it's something that has both a magnitude and a direction. Both a magnitude and a direction. I think on your notes I wrote no instead of both. So I apologize. It's a typo to be made. Okay, but there's both a magnitude and a direction. The magnitude is the actual amount, the value. The direction is what it sounds like, a direction, usually given with an angle. So you might hear, how many people have been on a boat before? Have you ever used boat directionals? Anybody know how to use boat directionals? Do you want to tell us about how it would work?
I know what they are. It's like forward, starboard, and then...
It's like red, right?
Those are directionals on the boat, but directionals for navigation.
Isn't it like red, right? Well, I'm just saying about the buoys.
That's possible with the buoys, but I mean like, how would you know where you're going on your boat? What do you use usually? Yeah, the compass tells you the direction, right? You're going north, you're going south, are you going west, are you going east, are you going 20 degrees northeast, 20 degrees, east-north? They're different things, northeast and east-north. Okay, so we're going to talk about that today with directionals. Okay, with directionals. So the direction and the magnitude. Now, the head of the vector's drawn with an arrow. That's why you see an arrow. It's called the head. The back of the arrow is called the tail. You don't really need the terminology, but I might use those words, so be familiar with them. Okay, it's not going to appear on like a test. So if we added two vectors graphically, imagine if I did this. Walk across the room all the way over here, okay, then I literally just turn right, and I walk all the way over here, and I stop right here. Now I started over by the podium, and I ended here. What could I have done instead of doing that to get over here?
Straight.
Could have done a straight line. What else could I have done?
You could have gone around.
That's zigzag. So there are an infinite amount of answers, right? I could have taken any path to end here, and they could all be different. Well, the idea with a vector is that the sum of two vectors is always the shortest path. Or if those two things happen one after the other. If I walk that way, then walk that way, I could get there by just taking the diagonal. That's what this is showing here in red. So a vector A, and I'll give you a demonstration in a moment. Oops. Vector A and B is equal to what's called the resultant. We always call that R. Okay, vector A plus vector B gives you vector R. And this has to do, if you recall, this is similar to displacement and distance. My displacement would be vector R. Take a look at the board. My displacement, if I started here and ended here, would be vector R. My distance would be what? A plus B. The distance traveled would be vector A's magnitude plus vector B's magnitude. So if this vector was 7 centimeters, this was 8, it would be 15 centimeters traveled. But this would not be 15 centimeters, okay? This would be 8 squared plus 7 squared equals r squared, and you could find the displacement. So the sum of two vectors is like displacement in a sense. Now, let's go to the next slide and take a look. So, the two vectors that you sum together do not have to be at right angles. They do not have to be at right angles, and they're clearly not, as you can see in this diagram here. So vector A plus vector B ends up being vector R again here. But in this case, vector A is drawn at some inclination. And then vector B is drawn at another inclination. And this is not a right angle this time. So what we're going to do in this section is talk about how to figure out the result of R, either graphically. So you put vector A here, draw it first, step 1. Step 2 is to draw vector B starting at the end of A. And then the resultant is from the beginning of A to the end of B. That's the resultant vector by connecting those two. These little arrows on the top just mean the word vector. Your textbook makes them bold instead of arrows. They use a bold font whenever something is a vector. So this is a graphical way to come up with the answer. If we knew how long this was and the angle, and we knew how long this was and the angle, we could also come up with this using trig. So we're going to do a graphical approach, and we're going to do a trigonometric approach. So let's take a look first at a graph. Let's see. How about somebody read that? Thank you.
A person starts to walk and travels 0.4 miles away before stopping for a sandwich. Then the person walks 0.2 miles east and breaks to read a book in the park for a while. After this, the person then travels 0.7 miles south and another 0.6 miles east. Graphically determine the person's final location with respect to the starting point.
So pick a starting point first of all. We're going to do this graphically. So pick something toward like the middle left over here. Let's make that our starting point. Now, we need to make some sort of a scale, right? What would the scale be in this case? What would the scale be? What do you think would be a good scale for this setup? Let me start with what do I mean by scale actually first. What do I mean by scale?
Like if you're like numbering the graph, like what would you use? Like would you go by 2, would you go by 1?
Good. So the values of change for each box on the graph. Yeah, what would the scale be, you think?
0.1?
Yeah, I would say let every box equal 0.1 mile. Because look at the distances in this problem, right? There's nothing more than 0.7. And we can figure out how to make 0.7 work for sure. We don't have anything greater than that. So let one box equal 0.1 miles. So what does the first leg of the trip look like? What does the first leg look like? How far? Good. So draw an arrow. 4 boxes up. If you need to, you can do this. You don't have to, but if you want to, you could put a little point there at the end, but you don't really need to. Okay, an arrow tip is fine. From there, what happens? What happens next, Honor?
0.2 miles east.
Good. 0.2 miles east is next. So 2 boxes to the...
Right.
Okay, I'll underline that in blue, actually. If you don't know east, west, north, and south, you need to come see me or literally read a book and figure out north, east, west, and south. I don't mean that negatively, but you should know that by now, right? East is right, west is left. If you forget, the word we, W-E, west and east. It's easy to remember which eye is which. Almost everybody knows north is up and south is down, but east and west, some students still have a tendency to mix them up.
We don't have the east. Just leave that out.
That works too, but think of the word we, W-E. The other way around would be ew. Right? Ew doesn't work. Whatever. Like north, south, west, east. So I think this makes the word we. Next, what happens after that? After the person breaks to read a book for a while. After reading that book for a while, what do they do next? What do they do next, Emma?
We go 0.7 miles south.
0.7 miles south. So let's go back to 4 boxes and then another 3 boxes down. Okay, 0.7 miles south. And notice everything is at right angles right now. In a moment, when we do this, I'm going to say the person walks 20 feet at an angle of 20 degrees northeast or something. So that gets a little trickier, and we need trig to do those, or a protractor at least. I'm not giving you a protractor right now, so we're going to simply do this. Last part. What does Joe Schmo do after that? I didn't give a name. Ellie?
The right.
How far? Okay, so we see the path taken. Now, before we go any further, if I were to measure, what would the distance traveled be?
Can I just count it?
What would the distance traveled be? Distance traveled.
Do you just like add up everything?
Yeah.
Yeah, that's what I thought.
19.
1.9 miles. 19 boxes. So 1.9 miles is our distance. We can jot that down if you want. Is the displacement going to be more or less than that? Clearly less, right? Remember, displacement is like the shortest path. So displacement will definitely be less. How do you find out what the displacement would be?
You just take a line,
Katie?
you draw a line,
From
starting point to ending.
starting to ending. Okay, so draw yourself a line. Now, how are you going to do that? You're going to do that with a straight edge probably, right? Okay, you're probably going to do that with a straight edge. So maybe take out your ID card or something that has some sort of a straight line on it that is not metallic. So like a plastic case of some sort. Okay, mine is a little bit off. I tried my best. So that thick black line you see drawn there is the resultant vector R. Okay, this is called the resultant vector R. R is your displacement from starting to ending. How can I figure out the length of R? It's not difficult. You have to just read between the lines here. Between the lines. Read between the lines. How do you calculate the length of R? Somebody who has not answered yet, please. Come on, let's go.
Calculate the length of like the side of each square,
And then?
and calculate how far is it from the beginning each point.
Okay, now
Like using the square as units.
you could use the squares as units. That's one way to do it. You're counting. But what about using something else? Is there another way to do it? Pythagorean theorem. Okay? Let's use Pythagorean theorem because it's, very obvious what we're going to do. So let's make a triangle, please. I'm going to pick another color. I'm going to go with brown.
Oh wow, there's so many colors.
There are. It's a color palette. So let's pick brown to redraw over here. And do we all see our right triangle now that exists? So, thank you. If I want to figure this out, I've got 0.3 miles and 0.7 miles here. Is it 7 or is it 8? I think it's 8, Theo. It's all right. So we have 0.3 miles and then 0.8 miles. So technically, one sec, Frank. Technically, this person could have just walked down 0.3 miles and walked over 0.8 miles, and they would have gotten to the same destination after only a mile and a tenth. But they walked 1.9 miles so that they could stop in the park and enjoy lunch and read a book and do all that other stuff. But at the end, it doesn't matter the path traveled. The displacement is still the same. Frank.
I was just going to ask, is this why we did the previous trig worksheet?
The what worksheet?
The trig worksheet?
Yes, we're going to use trig on this now. Exactly right. Yep, you're seeing it already. Good. So let's go ahead and figure out the resultant first. I'm going to get 0.73 for r squared. So what does r turn out to be in this problem?
0.85.
Theo, is that you said too? Agreed? 0.85? Good. Others can check this, please. Check your work. A squared plus b squared equals c squared. Here's the sum of a squared and b squared together. Should be 0.73 equals r squared. How do you get rid of a square?
Just kidding.
Square root it. Square root it. Now, one thing to notice. When you square root a decimal, it gets bigger, which is the opposite of normally square rooting, right? If you take the square root of 16, it gets smaller, it becomes 4. When you square root a decimal, it gets larger. Don't let that confuse you. You'd be like, oh, that must be wrong. It's true. Okay, a decimal gets bigger when you square root it. When you square a decimal, it gets smaller, actually. It's like 1/9 times 1/9 is 1/81st. Okay? So, anyway, back to the point we're looking at. We have what? The magnitude so far. We have the magnitude. It's 0.85 miles. What do we still need to really describe this vector? A vector has two things, a magnitude and a... Yeah.
Okay.
Direction. Direction. Go back to your first slide if you forgot. A vector is defined as a quantity that has a magnitude and a direction. We have the magnitude. The magnitude is the actual value of the path traveled. The question now is, what is the direction? So, before I actually answer that question, let's talk about directionals. So I'm going to scroll down. I'll come back up to this in a moment. Okay? I've got my 4 directions, right? Technically, imagine every time that the starting point is the origin. Okay? So this person started here and ended up down here. Because this person went down 0.3 and went over 0.8. Now in reality they didn't do that, right? We know that. This person really took this crazy path. But that's the initial and that's the final point. So, if I want to give a directional, always think about the angle with respect to the x-axis. So draw yourself a vector here, and then draw the angle in that would connect it to the x-axis. Look at the angle that I just drew on the screen. That's the angle that we're looking for in this problem. We are not, and don't draw this one please, look up, but don't draw this. We are not doing this angle here. See the angle in blue? The angle in blue is the angle with respect to the vertical. Whenever you're giving directions, it's always with respect to the horizontal. So if I were giving directions here, I would say that this person walked 0.85 miles south of east at an angle of blank, whatever that is. How do I know it's south of east? What does that mean? South of east means you go east, but it's south of that. Northeast means you go east, and it's north of that. East of north means you go north, and it's east of north. So if you heard somebody say the angle is 25 degrees east of north, it would be like this. That's what 25 degrees east of north means. But 25 degrees north of east means this angle here. See what I'm saying? Northeast literally means, put the word of, please, between them. Every time you do this, put the word of between the compound word northeast. North of east. You go east and you go north of it. That's where the angle would be. Here in our problem, we had to go east and then we had to go south to get there. So it's south of east. This angle here is south of east. So already I know that for this answer, it's going to be 0.85 miles at some angle south of east. My goal is to fill in that blank. I need to figure out what that angle is. So I need to figure out this angle right here. Well, if we go back, we had a triangle a moment ago. Didn't we have this triangle right here? See the blue I'm drawing? Look up. We had that blue triangle a minute ago. So if I scroll back up, I can see it a little more clearly, right? So this is like my horizontal axis again. Everybody see the dashed line I just drew across? I want to know the angle of declination or decline or depression. This angle right here, theta. What could I do, Theo?
You could just make the triangle, so you could just make it again, but with the top bit, you could just make it with the top 8 thing, and then you could use, Socotoa, I used tangent, and then what happened is I then did opposite over adjacent, and so tan equals, and then I got 20,
20 what?
well, at 20.6.
20.6 degrees. So again, Theo said just continue to make the triangle. Put this leg right here. Put this leg right here. Well, this is really a rectangle. So these are the same as these. Now, what else could you have done?
Oh wait, I didn't use decimals.
It's the same thing. It's proportional. 0.3 over 0.8 is the same thing as 3 over 8. What else could I have done instead of finding that angle directly right here? Remember, take a look up. I'm finding this angle right here. What could I have done instead? Ooh, Mr. Hall is going to be upset.
Instead of like recreating the triangle, you could have just found the angle of the original triangle because they're congruent.
What are these called? What kind of angles are these?
Alternate.
Nice. So he'll be happy. Never mind. Okay, good. I can tell him you guys remembered. Alternate interior angles that are cut by two parallel lines. This line is parallel to this line. This is like your transversal coming through. These angles are going to be identical. These two angles right here and here. This angle up here is going to be the same as this angle right here. But this is the angle that we're focused on right here. So technically we could have found this angle. And think about it. If you use this angle, right, look where I'm pointing. If I use this angle, the tangent function is still opposite over adjacent, which is the same thing we get by using this triangle. So how do we get theta by itself? Press second tan 0.3 over 0.8 and see what you get for theta. Yeah?
I was just going to say, couldn't you solve it by, you would find the tangent of the top left, like you would find the degree of the top left of like the black triangle, like the top left
sure.
there, and then subtract
from 90
from it.
Anthony makes a good point. You could have found this angle here directly in this triangle because you have these two, right, in this triangle. If you found this angle here, it's going to become around 70. Subtracted from 90 gives us around 20 for this answer. Very good. So he found the complement of this angle. So that's another way to do it. There's many ways to do it, but your goal is to find the angle between the resultant, I'm highlighting it right here, between the resultant and the horizontal axis. Recalling that the horizontal axis always goes through your starting point. Frank.
How did Anthony do it again?
How did it say again?
How did he do it?
Anthony said, why don't we find this angle here? And that would be 0.8 over 0.3 would be for the tangent. You get about 70, and then 70 from 90 would give you the 20 that's left over that Theo was telling us the answer actually is.
Okay, cool. Yeah.
So like if you would say, what would you say that you moved like?
So you would say that the resultant is 0.85 miles at 20.6 degrees southeast. If I read that statement, I would know exactly what to draw as a result. Personally, here's what I would draw if I saw this. My origin would be here. I know it would be southeast, so I'd go east. I'd go south of east. I would draw at an angle that's around 20 degrees. That's this angle. It's around 20.6 degrees. And I would label this as 0.85. Okay, so my vector here would look like that, right there. Okay? Now, before I move on to the next thing, because I think we're what time is the period over? Okay. Before I move on to the next thing, because the next thing is going to be different, I want you guys to, let me see. Okay, we can go to the next slide, because it's not different, it's one after. Tonight I want you guys to do the first homework problem on this homework assignment. Okay, so there's about 5 homework problems. Just do the first one on this to practice. Say again? Number 4, page 91, I think it says.
You put it on Dropbox?
No. Just do it tonight, though. But please practice. Don't just not do it. Okay, I want you to make time for tomorrow. Vector addition is commutative. And make sense of this, please. Right? Think, if I'm here and I cross Lex, right? Here's Lexington Avenue. I cross Lex. Look up, please. Then I cross 83rd. I would end up on the corner here. Or if I cross 83rd first and then cross Lex, wouldn't I still end up in the same corner? So vector addition, A plus B, is the same as B plus A. The resultant is still this purple line. So next class, next part of this section on vectors is really what's most important. We did the graphical analysis, right? We looked at the way we can use a graph to literally draw it out and see what happens. And that works. But really, with math and with physics, the algebraic approach, which is what we're going to look at, the trigonometric or algebraic approach, is really the one we're going to utilize more. Because most of the time, things don't go at perfect 90 degrees. Like that example we did was perfect 90-degree angles and stuff. It's not going to happen often. And you're probably not going to have a protractor to draw that angle and do it all graphically. And honestly, it takes forever to do it. It's much easier to do with trig than with a little bit of math. So let's go over how we're going to do that today. So, what we'll notice is this. Every vector, so vector A is our vector we're looking at. Every vector has what's called a horizontal and a vertical component. And that makes sense. Think about it for a second. If I were to use one of these objects as an example. If I were to take this ball of thread or whatever it is, roll of thread, and throw it like a softball planet. Okay, Willow, you're a pitcher, aren't you? Yeah. So Willow, when you throw, you release usually at the bottom of your arc so that it goes horizontally. For the most part? Okay. If I'm wrong, I'll just say it's for now. So you release at the bottom, you let go, and it usually travels horizontally. So I would say that the vector is all in the horizontal. The example on the test where Liam headed the ball up, or the example in the notes where the volleyball player is setting it, it was all vertical. But real life is rarely all horizontal, all vertical, right? Even pitching baseball and softball, there is some vertical component. A baseball pitcher will throw the ball, and as he throws it, it actually decreases in height because he releases it up here, yet the ball somehow ends up here. So it must decrease in height, right? A softball player maybe is a little closer, but they release down here, and it probably crosses here, so it probably rises a tiny bit. So there's always going to be a vertical and horizontal component to things unless they're fixed on a track. Right? Like a train on a track that's on level ground is only moving horizontally. But if there's any inclination to that track, the train is technically moving horizontally, and a little bit vertically, right? So that's what we're seeing here. So imagine I take this now, instead of throwing it horizontally or throwing it straight upward, I throw it at an angle. It moves with some sort of projectile motion, some arc or arched path along the way. And what we're going to see here is that this vector here is like me throwing it initially. I'm throwing it vertically and horizontally. We saw the particle move up, and we saw the particle move over. That's what these are representing. So, if I have a velocity in a problem from this point on, we're going to have to break up that velocity into its vertical and horizontal components. So if I kick a soccer ball, and I punt it, or Turks punts the ball out from the goal, and it goes at an angle 30 degrees, well, part of his kick is out, and part of his kick is up. Think back to football, American football. Anybody follow American football? No. So what's the goal, Frankie, for a punter? What does a punter usually want to do, generally speaking, when he punts the ball?
Get it to the other side of the field or to get it in the field goal.
Yeah, so if they're kicking a field goal, they go to the field goal kicker, but if they're punting it, they want to get it together in the field. Exactly. Now, what's the goal for a punter specifically? What does he want to really get it to do?
Travel the most distance.
And what else?
Height.
And height. So a punter wants to maximize his hang time, right? Hang time is the term. So that what happens? As the ball's in the air, his players can do what? They can run down the field and bring his tackle down, right? He also wants to have a long trajectory so that it actually goes like 60 yards. But you can't have both, right? You really can't have both. So usually the punter finds some sort of a compromise. This punter will kick it far, but also high. If the punter kicked it straight up, it might be in the air for like 10 seconds instead of 4 seconds, but it's not going to go anywhere. It's going to be a 20-yard punt. If the punter kicks it 80 yards, which a lot of punters can kick easily 80 yards, they want a lot of hang time. The guy will catch it, he'll be able to run 30 yards back before he even gets touched by a player. So an 80-yard punt becomes a 50-yard punt then, right? Or 70 becomes 30, whatever it may be. So the goal is, though, to kick it horizontally and vertically. So we want to determine today how to figure out those components. So let's go ahead and do that. Let's use trig to do that. So let's take a look and let's figure out what our trig functions would be to represent the horizontal and vertical component. So let's look now at the horizontal component with respect to the vector A. If I wanted to set up a function, is it sine, cosine, or tangent for these two here? Again, for the horizontal component and vector A, would I use sine, cosine, or tangent for this angle again? Venom?
Tangent.
Not tangent.
We're trying to get the vertical component and the horizontal component. I mean, we have both of those, and we're trying to get the hypotenuse, right?
Let's say that we're trying to write a relationship that relates the the vector A and the horizontal component.
Oh, vector A and the horizontal component would be the hypotenuse and adjacent, which would be cosine.
Okay.
I was like 4 seconds away. We need to figure it out. Take it away from
All right. So we have cosine and adjacent and hypotenuse. Now, the adjacent side is the horizontal component, so let's write this out. Cosine theta equals horizontal over vector A. Equals horizontal over vector A. Now, what if I wanted to know, because you're going to need to know this for this next section, What if you needed to know the horizontal component specifically? You need to know the horizontal component, right? Make believe we're trying to figure out what that is. How do you solve for horizontal in this equation? Remember, horizontal itself is a variable, right? This is x, this is y, and this is cosine of theta. How would I solve for the numerator in this fraction? What do I do to get the numerator by itself? How do I get rid of this denominator? Okay? Multiply both sides by vector A. Multiply both sides by vector A. What happens on the right-hand side? Vector A and vector A cancel. So it turns out that vector A, or whatever vector you call it, doesn't matter, times the cosine of theta is equal to what's called the horizontal component. This is always going to be true. This is going to be huge, especially even for your math class. Mr. Hall is he's going to love it when you come in one day and he goes to go over this and you're going to be like, we know this already. You want the horizontal component? Easy. Just multiply by cosine theta. Whatever your vector is, if you want the horizontal component, just multiply by cosine theta. All the time. Now, we're assuming that theta is the same angle always, the angle between the vector and the horizontal. Remember yesterday I talked about that? Theta is always the angle between the vector of interest and the horizontal. It's not the other angle up top. Okay, it's not that angle up in the top right of the triangle. So this is always going to be true. So if you want the horizontal, it's always going to be vector A times cosine, yep? And you can guess to the next part, but what if I want the vertical? What do you think it's going to be?
Sine.
It's going to be sine. Let's prove that's true. So let's write that down in the next part now. If I want to figure out the relationship, and Benno did this a moment ago for us, if I want the relationship between the vector A, which is hypotenuse, and the vertical component, which is opposite, right? Opposite in the triangle. We have opposite and hypotenuse. Opposite and hypotenuse. So we go ahead and say sine theta equals vertical over vector A. And take a look and look at the similarities, folks. I'll put a line to show the difference that we're on the next part. But look at the similarities between this right here and this right here. It's really the same thing, but where you have horizontal, you have cosine. Where you have vertical, you have sine. So if I want to solve this for vertical now, again, I'm going to multiply, as Natalie told us a moment ago, multiply both sides by vector A. Vector A's cancel, and that tells me that if I want to figure out what the vertical component is, I could say vector A times sine theta, and that equals the vertical component. Come on, Anthea. Okay, and that equals the vertical component. So again, I want to multiply my vector by one of the trig functions, either cosine or sine. How do you remember which one to do? Alphabetical. Horizontal comes before vertical, right? Alphabetically. Cosine comes before sine. That's how I remembered it when I was in high school. It's very easy to remember it that way. Yeah. Okay, so the easy memorization. Whenever you want a component of a vector, multiply by either sine or, God bless you, either sine or cosine. Does that seem? Either sine or cosine. It doesn't matter which one, honestly, as long as you know which function you're on. But you're never going to use tangent for this. Okay, we'll talk about where tangents come into play now. Okay? Questions? Yeah.
So if you have like the number 5 as your vertical, and like you want to know your vector A, but like if 5 is like the only number.
You would need the angle also, and you'd have to divide by that to get the vector.
What if you were
Can't. It's impossible. Okay? So that's a great question. You could be told that the vertical component of this is 5, and the angle is 20 degrees. You can find out what the vector was. But usually in this class, it's going to be this way. You're going to be given the vector. So imagine I give you that the velocity of a ball is kicked at 40 meters per second at an angle of 20 degrees. If you want to know what the horizontal component of velocity is, you take 40 times the cosine of the angle, which was 20. That gives you the horizontal component of the velocity. We're going to see that in section 3.3 though. It'll be a little more clear with velocity, all right? But this idea, and you could either circle or box these in, this idea here and here, it's not on your formula sheet because it's not a formula. It's a result of solving trig functions. But you don't want to solve these trig functions every time, do you? That's a lot of work to do it every time. So memorize it. Remember, alphabetical. If you want the horizontal component of the vector, take it, multiply it by cosine. If you want the vertical component of a vector, multiply it by sine. Okay? All right. Let's see. Let's take a look at revisiting this graph that we had earlier. Take a moment and study this diagram. Try and figure it out on your own what it means. You can do it. You guys are smart. Figure out what it means. Figure out what all these markings are in the diagram. Try to determine, somebody can explain to us what's happening here. Who thinks they can explain to the class what this diagram is illustrating? Katie, I'd like you to do it. And Katie, when you do it, I'm going to point and show what you're talking about, okay?
So in the second diagram, it's showing instead of taking the triangles on the inside of the triangle given, or instead of taking the measurements on the inside of the triangle given, they're making triangles from the lines A and B. And then...
What is this?
Oh, that's just what we were doing before.
Magnitude
Yeah.
and direction. Okay, keep going.
And then in the second diagram, or in the third diagram, it's showing the two kind of connected.
Correct. Where did these come from though, Katie? Go back to the second first. Second diagram. Where did this value come from? AX.
Is it just the amount?
But where did it come from? How did they determine it? What did we talk about in the last slide? How did they determine the X component or the horizontal component?
With units, whatever they are.
What do you mean?
Because they probably just chose a unit for its use.
But they did, that's one way to do it graphically, but using trig, how could they do it? Let me rephrase that question, because yes, using the graph, they actually gave a scale and picked out what the units were. But what about if I wanted to do it with trig?
You do vector A times cosine.
Yeah, so what's vector A's measurement? Isn't it 12 right here? And the angle is 20. Go to your calculator, please. Type in 12 times cosine 20. Type in 12 times cosine 20. And again, it should not be like, oh my gosh, because on the diagram, it should be easily 11.3. So if you think about this, to figure out the horizontal length of A, it's called the projection really in engineering, a projection. If I took, imagine, I can give a good example of this if you ever want to think about it. Ready? Take the iPad, go like this. You could try this at home. Actually, extra credit. I do this a lot, by the way. I haven't done it this year yet. So I do extra credits, and the extra credits, here's how they work. I give you an assignment outside of class. You have to do it. You have to record yourself doing it with a video, and you have to explain it. And then just put it in Dropbox. Okay? So here's what you're going to do. explain what you're doing and how it works. I want you to go home. Okay, you might need help with another. You can work with another person. That's fine. But I want to know that who's working together. So go home. Take an object like this, something that's rectangular. Okay. Put it at an angle. Measure the angle. Take a flashlight and shine it down directly above. When you
flashlight, or is that like a real flashlight?
a flashlight.
Okay.
Take a flashlight, shine it down from directly above. What will it produce? It will produce a shadow right below it. The length of the shadow produced is our AX. So if I shine a flashlight here, the length of this shadow from here to here is what AX is. Now, that's going to be the easy part. The hard part is going to be, take it now at the same angle and put it up against the wall. Shine a flashlight against it like this. The height of this shadow here is going to be your AY. Measure those lengths. So measure the length of the object you're using. Measure the length of this shadow here. Measure the length of the shadow here. Come up with those measurements in your video. Show me you're measuring it. Then prove that that's true using trig. So this will take you 15, 20 minutes. Not like an easy thing. But that's the way I kind of give extra credits. I give videos to do this stuff. And I give extra credits. I usually put like a point or two, depending on how well you do it, on a test grade. So it's either like a point or two. If you don't do a good job and you still do it, I'll give you like a point because you kind of did it. But if it's not a good explanation or you didn't do all the things I wanted, I won't give you that second point.
What
Okay?
if it's like so good it deserves
If it's amazing, maybe I'll give you 3 points. Who knows? You know? Who knows? All right, enough. Don't be greedy then.
It's on a test.
So yeah, I put it on a test. Okay. So again, simply take a flashlight, shine it from above. Measure this length of this shadow before the end of the quarter. Measure the length of this shadow. Take a flashlight, shine it from the side. Measure the length of the shadow on the wall. Okay. Know the angle that you're measuring. Then go ahead and calculate AX and AY from the angle and the length and see if they're the same as the shadows. And if they're not, it's okay. It doesn't matter. It doesn't have to be exact because the shadow's light might propagate outward a little bit. So it's okay if it's not identical. But I want you to show me that you did it.
And is this 3 points like
No,
a-
1, 2, or 3 points.
Raw score.
fraction or
The fraction.
To the numerator.
So you add it to
That's
the
good. That's not
numerator-
bad.
You add it to the numerator and the fraction?
That's what I usually do.
But then.
Because I keep, in my grade book, I have your raw score written down. I don't have your percentage grade
So
down.
you don't add 3 to the denominator.
No.
Well, you could do that. Add 3 to the denominator and
Sure.
3 to the top.
It would go up only slightly then.
Yeah.
Yeah.
Oh, you
No,
can
no,
play
just to the
something
top.
like that.
All right, so AX, again, the horizontal component or the X component comes from vector times cosine. How about the 4.1? Everybody? What about the 4.1? What are you going to do for that? Okay, you can do Pythagorean here, but just use trig. What would it change to? Sine. Go ahead and do 12 times sine of 20. And you're going to get, good, 4.1, which is given on the diagram. Now, here's what I want you to notice. Vector B, the same thing has happened. But now vector B's, its angle is a little bit, not different, but it's a different measure. The measure of angle B, or vector B, is 25. The angle vector B acts at is 60. Okay, where am I looking at, right? I'm looking at the top of the page right here. Vector B is 25 units long. We can see it's much longer than vector A. The angle is much greater. This is an angle of 20. Where is the 60-degree angle on the diagram? Yes, it's right here. Please draw that in so we know that that's what that means. That's theta B. Okay, the angle between the vector and the horizontal is always the angle. This is no longer the horizontal. For vector A, yes, this was the horizontal, right? For vector A, the bottom of my graph was the horizontal. So the angle for vector A is right here. That's an angle of 20 degrees. This is a much greater angle right here. It's 60 degrees. That's theta B. This, it's hard to draw it. I'm going to zoom in a minute for a moment. Right here, that's theta A. It's hard to see it, but that's theta A right there. Theta B is the vector to the horizontal again, not to this horizontal here. Is that clear what I'm saying? The horizontal that is created from its triangle. Let me zoom back out so you can see again. And what we're noticing is this. If I could calculate the horizontal component of vector A, and I can calculate the horizontal component of vector B, if I add those numbers together, I get 23.8. If I add the vertical components together, I get 25.8. I can then use what to get the resultant? How can I get the resultant from this information? Pythagorean theorem. Okay? So this is vector addition with trig. With trig, you want to add the horizontal components of all your vectors together, add the vertical components of all your vectors together, and then you end up with a triangle at the end. It will always look like this. You'll have a triangle like this. It doesn't matter if there's 7 vectors. You're still going to have a triangle in the end. You then use Pythagorean theorem to get r. How do you get the resultant angle? How would I have gotten this? I'm going to point it out. The resultant angle. How do I get that? Which trig function would you use? You know opposite, and you know adjacent.
Okay,
10. Okay, so to get this angle that's missing here, you would do, and I'll do it at the top, you would do the tan of theta equals opposite, which is 25.8, over adjacent, which is 23.8. It's really what? Isn't it just vertical over horizontal? Make sense of this, please. The tan function is really just going to be used, and you're going to have vertical, 25.8, over horizontal, 23.8. It's opposite over adjacent, yes, but you could start utilizing the fact that it's always going to be y over x. Vertical over horizontal. Okay? Vertical over horizontal. Do the tan inverse to get the value of theta. What do you get for theta?
Wait, 47.3.
And it's always going to be an angle between the first two that you used. The first angle you used was 20. The second angle you used was 60. It's not going to be something outside of that range. Okay, because 47, it's not an average. It's actually what's called a weighted average, but it's weird to actually calculate that without trig. Okay, so you wouldn't just average 60 and 20 together and get 40. Okay, so what did you say again? What was it?
47.3.
How did you find 47.3?
Tan inverse 25.
Come on. We've been doing this, guys, for like 3 days now. When you want to find an angle, use the inverse function. Press in your calculator, second tan, type in 25.8 over 23.8, then hit enter. If you're not in the right mode, you might not get the same answer, which means you need to change the mode of your calculator. 47.3. Ellie, good? Okay. Questions on this example here that we went over together? Frankie, you looking at your question? The tan part?
Yeah.
So, what we recognized first was that this horizontal component plus this horizontal component gave us this, right?
Yeah.
This vertical plus this vertical gave us this. So this is our resultant triangle. So we can calculate r by using Pythagorean theorem if we wanted to. But if I want this angle here, I need to use opposite, it's this length, over adjacent, which is this length, which is the tan function. Tangent equals opposite over adjacent. To get theta by itself, do the tan inverse of this side. Okay, we're going to do another example in a moment. Okay? Let's see. Yeah, let's do this next example.
Let's see.
I think I got this one. I'm not sure if I got it right or not.
Here, while I'm going over, check your answer if you did already. So, we got, you want to read? Yeah, go ahead.
John starts at the southwest corner of Central Park and walks at an angle 30 degrees north for 0.8 kilometers and then stops. He eats lunch and enjoys the wonderful weather before heading 25 degrees southeast for 0.5 kilometers from that point. Determine his overall displacement.
Displacement. Now, oh, thank you. There should be a period there. Displacement. So, John starts at the southwest corner. So, where's my starting point? Southwest corner. This is Central Park. It's my great illustration. Now, he walks for 0.8 kilometers. 0.8 kilometers. I don't know how, I mean, Central Park across is around 0.7 miles, by the way, across this way, directly. This is in kilometers. 0.8 kilometers is, let's see, it's 3/5. It's like probably less than 0.6, around 0.5 something miles. Whatever, it doesn't matter. But it's 0.8 kilometers, okay, at an angle of 30 degrees northeast. Where's that? Here's east, right? What's northeast? Show me with your arms, please. Yeah, that way, like that, right? So here's east. This is north of east. Here's east. This is south of east. So the angle 30 degrees is right here, between my arm and the horizontal. So go ahead and draw on my arm on your page. Okay, draw an arm, or draw a length in like that, an arm. Wow. Let's label this as 0.8 kilometers. And label this angle as 30 degrees. What does he do next? He stops, he hangs out, he eats lunch, has a good time with the weather. And then what does he do? From that point, right? So here's what I'm going to do. Watch what I'm going to do, folks. Put a dashed horizontal line here. That's your new horizontal. A moment ago, the horizontal was the bottom of Central Park, right? But this guy is no longer on the bottom of Central Park, so that's not my horizontal anymore. You need a new horizontal. And I need to go southeast of that. How do I go southeast? Well, I think about, if I went east, it would be this way, right? From here, look up. From here, directly east would be this way. Southeast means I'm going this way. So this person is now coming back down at an angle of 25 degrees for 0.5. So make it a little bit shorter, please. Question is, where does he end up with respect to his origin, or determine the overall displacement? Same question, right? So our goal is to find out not only the length of this red line here, but the angle at which he ends up. So our goal is to figure out r and theta. Our goal is to figure out that angle theta and the length of the red line r. So we need to do this like we did the last problem. So everything needs to be broken into its components. So the 0.8 kilometers, we need to know what this x length is right here. I'm going to highlight it in blue. Take a look. I'm going to put down a spot here that matches up. See how this matches up with this right here? Draw like an imaginary vertical line if you need to. But this matches up right here. I want to know this horizontal length. Shade that in blue, please. How am I going to get the horizontal component there? How am I going to get this? What's the formula I'm going to use from the last few slides we've been doing? How do I find the horizontal? Take the vector, multiply it by cosine. So 0.8 is the vector times cosine of 30 degrees. That'll give me that length right there. Do we all see what I'm saying right now? I want the horizontal part of it if I were to shine a flashlight from above. Now, if I want the vertical part of it, which goes up to here, on the side, look at the y-axis now. If I want that vertical height, what do I do? Good. Oops. So the height of this is 0.8 times sine 30. The width of this vector is 0.8 cosine 30. I'm going to need those numbers in a moment, but for now, leave it for now. We'll come up with those in a second. How about the second vector? Let's use purple for the second vector. For the second vector, it goes from where the first vector ended, right here. See, right here, to where it ends. So draw another one here. That's the horizontal component of the second vector. And what will that be? What would the horizontal component of the second vector be mathematically? Go ahead.
Is it the inverse?
Not inverse, no. Same thing we did for the last one, guys, but instead of 0.8 and 30 degrees use its numbers. Emma? Very good. Again, this is literally the same thing, except instead of 0.8, now it's 0.5. And this is cosine 25 instead of cosine 30. Now, the other part goes from here in purple to here. And I'm going to highlight this region right here. What is that length?
0.5 sine 25.
Now, what's interesting is this. When we add these together later, what do we have to do to that last part that we just wrote? Remember, he walks like this. Ready? Follow me. He walks northeast, but then he walks southeast.
Negative.
Yeah. This is going to be a negative component, actually, because he's moving south, which is negative. East is still positive. So these are all positive because these are east, right? These are eastward motions I'm pointing to right here. Eastward, so those are positive. This was a northward motion, but this, once he got up to here, he moved back down. He moved down. This is south. So this is going to end up being subtracted. So here's what I'm going to do. Ready? For the x direction, I have 0.8 cosine 30 degrees plus 0.5 cosine 25 degrees. This is what was on your last slide. Remember, on the last slide, this length and this length were added together. We're going to do the same thing. Add the two x's together. And then in the y direction, what are we going to do, though? What are we going to do in the y direction?
0.8 times sine 30.
Good. Now we're going to use sine instead of cosine, but the exact same numbers. And there's one other difference. Minus. And that's only because he walked back down south. It has nothing to do with it being y versus x. It's not always going to be a minus for y or always a plus for x. But because he walks south, we're losing that y direction now. It's a y displacement that's down, which is a negative value. What did I get for my numbers, Ant, when I added these?
You got, for the hypotenuse?
For x and y, the sums of these. It's on my sheet.
1.15, y 0.19.
Let's make sense of this, please. Look at the resultant vector. Follow the board where I'm pointing here. The resultant vector is mainly horizontal. It's only up a little bit. So this length right here, take a look. This right here is 1.9. Or 0.19. This is 0.19. This is 1.15. Use Pythagorean theorem with this little triangle to find the resultant right there. Okay, your homework over the weekend is to finish the rest of this.
Mr. Howard?